there, and this welcome to this session for physics at Sinal classes. We will be starting with the subject of kinematics today. So, as this name suggests, kinetics or kinematics is the study of motion. So, in this particular branch of physics, we formulate the equations and the variables and relations between them, the definitions, etc., which are related to motion of a body, without getting into the cause of motion. So essentially this subject just deals with how to represent the various variables of motions or the parameters of motion, how they are related to each other, and through that formulate equations through which we can make time predictions in how the motion will progress. In other words, that if, for example, we know that a body is moving at a given point of time, we are aware of its direction of motion and the rate at which the displacement is changing. In other words, we are aware of the velocity. For example, based on that information, we can predict that after a certain period of time, provided the velocity does not change, where the position of the particle would have changed to. Or suppose we know that the velocity is indeed changing, but it is changing at a constant rate. Then by making use of the mathematical tools of calculus, that is rate of change and differentiation and integration, etc., we can again formulate through the information about the acceleration of the body, that is the rate of change of velocity, what the velocity would be as a function of time, and thereby we could find out what the displacement or the position would be as a function of time. So that is basically the root purpose of the subject. Now, as far as the general type of motion of a body is concerned, and again considering the general type of body to be a rigid body. So for example, this pen that I have over here is a good example of a rigid body. So what we mean by a rigid body, of course, is that it is a body that consists of multiple particles, obviously in this case millions of billions of particles, and rigid essentially because these particles are rigidly attached to each other. That means the orientation of the particles could not change with respect to each other. So in very simple terms, what I would say is that if you consider this pen as a rigid body, and you just imagine the different letters that are written over here, like there's WHITE, white, written over here. Just imagine in your mind as if each of these letters represents a different particle. Now as you can see, because the pen is a rigid body, even though I can move it, twist it, rotate it, etc., the orientation of the different particles, or in this case namely the different letters that are written, you can see it visually, that the orientation is not changing with respect to each other. So thereby I would define this body as a rigid body. Whereas, for example, if this pen was made of something elastic like rubber or chewing gum, then I could create a situation in which I twist it and I put it under stress in such a way that the mutual orientation or the distance, etc., between the different particles, or in this case the different letters, would change. The shape itself would distort. So that would be an example of what we call a rigid body, a non-rigid body. So at the outset, of course, in mechanics itself, and the portion of physics we are studying comes under the general category or classification of mechanics, Newtonian mechanics to be precise. So in the outset of our study of mechanics, it's very important to understand the classification or the difference between what can be classified as a rigid body and what is a non-rigid body. Of course, our concern here right now is with rigid bodies. So a rigid body is a collection of particles which are rigidly attached to each other, hence their mutual orientation does not change during motion, displacement, etc., application of forces, etc. Right, so of course we will not worry about the non-rigid bodies at this stage, so keeping the discussion limited to rigid bodies. Now further, when we talk about the motion of rigid bodies, we can see that in the most general case, the motion can be a pretty complicated situation of what we say is a combination of rotation and translation. So for example, if I fling this pen like this, so what I would see is that it would be traveling like this. See, the pen, if you fling it in a certain way, what we would see is that more or less the center of the pen, or what we call the center of mass, would travel just like a cricket ball or something like that would travel, a spherical body would travel. But the motion of the entire rigid body would not exactly be like that. there would be certain particles within the body. For example, take the end of the pen to be a particle. It would have a rather complex kind of motion, because as the pen is traveling through space, or in this case through air, you can see that the body itself is rotating about its center of mass, while the center of mass is in a certain kind of translation. So this kind of motion can be extremely complex, and we call it the general motion of rigid body, which is a combination of rotation and translation. So obviously the ultimate aim being to be able to express this complex type of motions in the formal language of kinematics, bringing it down to a set of equations, formulations, etc. However, the process is stepwise. So what we would do in the case of general rigid body motion, which is combination of translation and rotation like this, is we would first write the equations of motion of the center of mass, just treating it like a particle, because its motion is rather simple. And then what we would do is we would write the equation of motion of the rigid body itself, but not in the ground frame, with respect to the center of mass. So imagine if somebody were, even as the pen is making this complex kind of motion, if somebody was traveling exactly along the center of mass, parallel to it, so the person has an exact identical motion as the center of mass, what would the person observe as the motion of the rigid body? The person would probably observe the rigid body to be just rotating like this. So that motion is something simpler to describe rather than the entire general complex type of motion. So that particular type of motion we will study at a later stage is called pure rotation. So pure rotation is when a rigid body is rotating about a fixed axis. If I get into the center of mass frame, in that particular case we were talking about, we would observe that the body is in pure rotation. So then what we can do is we can explain the entire motion of the rigid body in the ground frame, this one, the complex one, as a combination of two things which are happening simultaneously. One is that the center of mass is traveling like this, like a particle, right? And we can write equations of motion of that. And while the center of mass is traveling like that, like a particle, the rigid body itself is in pure rotation about the center of mass. So when you combine the two things happening together simultaneously, you can see that we have this sort of motion. Right? So that is the ultimate goal of the subject of kinematics, to be able to write equations that significantly and completely describe all sorts of motions of all sorts of bodies. However, we'll take it step by step. So at this stage, we will be discussing a type of motion which is called pure translation. In context of rigid body. So pure translation is a simpler type of motion as compared to the motion we were talking about earlier, where there is a combination of linear motion or translation of the center of mass and rotation about the center of mass. So what happens now, just imagine another situation where this particular rigid body is not traveling like this, rather it is traveling like this. So it's traveling in such a way that if you get into the center of mass's frame, that is again you are traveling parallel to and identically to the center of mass, you would not see the rigid body in motion at all. So that basically tells us that each and every particle within the rigid body has an identical type of motion, an identical trajectory, an identical path at any given point of time. It has the same speed, velocity, etc. At any point of time it has the same displacement as any other particle. So when that happens, we describe the motion as pure translation. So pure translation of a rigid body is defined as motion such that every constituent particle has a motion identical to the center of mass. Of the rigid body. So in this type of motion, why I'm saying it's much simpler is because each and every constituent particle of the rigid body has an identical motion. We don't need to describe anything separately for them. Whatever are the equations of motion for the center of mass or the center point or any reference point within the rigid body, if we write equations of motion for that particular particle or that particular point within the rigid body, it suffices, because each and every other particle has identical motion as that. So, a good example of translational motion of a rigid body would be a vehicle moving on a road in such a way that it's not skidding in any way. So it does not take any rotation about its own center of mass as the vehicle is traveling on the given route, let us say. Or another example of pure translation of a rigid body would be basically the motion of an aircraft, but at a point of time when the aircraft is not flipping like this, it is going in a purely translational motion like that. Or the motion of a rocket as it takes path, or the motion of a cricket ball or a baseball or a football as it is making a flight through air. Of course, footballs can also be can also be kicked in such a way that they are spinning as they are moving. So we don't want that to happen in the case of pure translation. So, for example, the motion of the Earth in its revolution around the sun is not an example of pure translation, because the Earth is at the same time spinning about its own axis. So in pure translation, we don't want that to happen. So in other words, you take a stone in your hand and you just throw it in the air. That's an example of pure translation. But you throw it in such a way that you've given it some spin. So as it's traveling, it's also spinning about its own axis. That is a different situation. That is not an example of pure translation. So we have understood the difference between pure translation and the general type of motion of a rigid body. And significantly, we have also understood why it is easier to describe pure translation in terms of equations of motion. And then, therefore, the task at hand next is kinematics, which is the study of equations of motion. So when we are discussing kinematics in this particular chapter, in this section, we'll be discussing in context of pure translation. Please remember that all the equations of motion that we learn to write, whether we are writing them for a single particle or we are writing them for a rigid body, which is a collection of particles, they are applying to a situation where it is understood that the rigid body is in pure translation, right? There is no rotation happening about its axis. Alright, so keeping that in mind, what we will do next is we'll understand some of the parameters or the different, you can say, variables that are connected to the equations of motion, or that are described by the equations of motion, and we will learn to relate them with each other at the next stage. So, start with something very simple. First one we start with is distance, and we can denote distance with a symbol d or s or whatever. Right. Now, what does distance represent? So in layman's language, when we say that a person has traveled a certain distance in a certain amount of time, the meaning that we have is actually identical to the physics definition of distance. It actually means the path length. Okay. So for example, if a person has been pacing around a room and constantly in circles, so after a certain amount of time, the person is back to where they started from. But we would not say that the distance is 0 because he's back to where he started from, because the person has paced, has traveled a certain amount of path length. So we would say that he has walked a certain distance, though he is not displaced. Whereas a person moving out of the room and walking to another location during the same interval of time, we would say that a person not only has traveled a certain distance, but the person has also been displaced. So we need to understand what is the exact difference between the two terms displacement and distance. Now, as far as the term distance is covered, it is simply defined as the path length traveled by a rigid body or a particle. So we define the distance as the path length, or the actual length of path. Okay. That is traveled by particle or body. So that is how we define the term distance. Okay. Now, of course, according to how we have defined distance, it is, as you can see, it's a scalar quantity. Secondly, it has dimension of length. Okay, or what we would say m to the power 0, l to the power 1, t to the power 0. So these would be the fundamental dimensions. Or the other thing is obviously the units. So the standard international unit is meter, and the CGS system, or the centimeter gram second system, the unit would be centimeter. Where we know that 1 centimeter is 1/100th of a meter. Right? Another common unit, for example, is kilometer. So 1 kilometer is 10 raised by 3 meters. Right? And obviously in the old British system, or the FPS system, another unit that was used were feet and inches and miles. Okay, wherein you know that basically 1 centimeter is roughly 0.4 times an inch, and 1 mile is exactly 1.6 kilometers, or 16 kilometers is equivalent to 1 mile, right? So that is the fundamental of distance. Now, obviously, one thing of note over here is that the distance traveled by a body is something that cannot become negative, or it cannot reduce with time. It always increases. So from the time we are from the instant of time, you can say, that we start recording the motion of a body till eternity, the distance always, either distance traveled can remain the same because the person has not traveled, or it can increase, but it can never decrease. So the length of path traveled by a particle can never decrease. So distance never decreases with time, right? So that's just a very intuitive idea, but something to keep in mind. So just take a note of that and take the next part up. Okay, now the next definition that I will look at is position. How do we define position of a body? You see, we are tracking the motion of a particle or a body. The whole thing makes sense when it is in reference to something, right? For example, I'm looking at the motion of a bus, and I'm looking at it as a person who's stationary, as a pedestrian who's stationary on the ground. It'll look like something to me. I'm looking at it as another person, let's say, who's traveling on a car that is moving parallel to the bus or anti-parallel to the bus, and the motion of the bus will completely look different. Okay. Or let's say I am sitting inside a bus, and there's a person who's walking backwards inside the bus, from the front of the bus to the rear of the bus. So his motion to me, as a person sitting inside the bus, will look like it's in the backward direction. Its direction is from the front of the bus to the end of the bus. But if that is happening, if that person is walking inside the bus, even as the bus is traveling at a high speed, simultaneously he's walking backwards. So to another person who's outside the bus and stationary, the motion of that person will not look like it's in the reverse direction. It will look like it's in the forward direction. So as you can see, even though we've already gone ahead with the description of distance traveled, we have to understand one thing, that the measurement of any of the kinematical parameters only makes sense when it is in reference to something. So when we start by describing position, we understand that position is described in relation to something called a reference frame. Now, what is a reference frame? A frame of reference or a reference frame is basically a system, a physically defined system, according to which we will make all such measurements of kinematical parameters. So in very simple terms, such a physical arrangement which we can use as a point of reference could just be visualized as a rectangular Cartesian coordinate system. So a reference frame in our context or in our within our parameters of study here in kinematics, a reference frame could just be simply thought of as an XYZ coordinate system with a defined origin. Now, if you're talking about a reference frame which is attached to the ground, it is stationary. So the origin would be stationary on the ground. The three axes would be stationary. If the reference frame happens to be traveling, for example, we are looking at the motion of a person who's inside a bus, and we're looking at it from the point of view of the reference frame of the bus. So in that case, just imagine the reference frame as a moving reference frame, and it is nothing but an XYZ coordinate system that is linked to the bus we're talking about, or it's linked to the moving object that we're talking about. So its origin is a moving object, and the coordinate frames or the axes are moving accordingly, right? So that would be an example of a moving reference frame. So as I said, I mean, whether a reference frame is considered as a moving one or a stationary one, at this stage we will just visualize a reference frame as a three-dimensional XYZ coordinate frame, right? So a reference frame can be thought of as an rectangular coordinate frame or system of axes. That is an example of a reference frame. Now, once we have a reference frame in place, it is very easy to define the position of a particle. For example, a very traditional way to define position would be just by giving the coordinates of a particle. So, for example, even the geographical location of bodies is usually given in a similar manner, rather than coordinates. They are called coordinates, but they are given in terms of latitude and longitude, which you can say is a way of grid mapping the space or the surface of the earth. So similarly, if the grid mapping that we are doing, instead of doing it in terms of latitudes and longitudes, it is in terms of an XYZ coordinate system with a defined origin, then we can define the position of any particle, for example, as a set of particles, as a set of coordinates, XYZ coordinates, that would represent the position of a particle. And if the particle happens to be moving, then obviously what we'd observe is that the coordinates are changing with time. Just like, geographically speaking, if we have a moving object, we know its coordinates are changing in terms of latitude and longitude, they are changing. So something similar to that. However, here we will see, for reasons that will become clear as we go along, vectors and vector analysis is very much an everyday tool, mathematical tool in our description of kinematical equations. So rather than take a coordinate geometry approach to defining the position of a particle, whereby we define it in terms of XYZ coordinates, we would define the position itself as a vector quantity. So in other words, we are now looking at position vector. So position vector, and we describe it usually with the symbol R, right? So the position vector, or rather the position of a particle, is defined as a vector denoted by R, and that vector is nothing but the vector joining the origin of our coordinate frame with the location of the given particle. So position vector for a particle is simply defined as the vector joining the origin of the reference frame with the particle. So, in other words, visually or geometrically we can understand position like this. this were to represent our XYZ coordinate frame, this point being the origin, and let's say a particle is right now located over here. So the position of the particle would be simply defined as this vector. So in other words, if the coordinates of the particle are x, y and z, we can also see that the position vector is defined as xi cap plus yj cap plus z cap. So obviously you can see that there's a correlation between the three-dimensional coordinates of the particle and the three-dimensional position vector. It's just a case of converting the coordinates into a vector using component algebra, right? So that is how we define position. Now obviously, as you can see, position is a vector quantity. It is defined in terms of the reference frame. So two things to understand about position. So position is a vector. And secondly, the dimensions of position are length or right. Third thing, what is important to understand is position is defined in terms of position is with reference to the given frame or with reference to where the origin of the given reference frame is located. So that is something important to understand about position. Okay. Alright, so the next very significant definition we will see is the quantity displacement. Now obviously in terms of definition, we define displacement as a very clearly defined or very easy to understand parameter, wherein the displacement is just defined as the shortest path between the initial and the final location, final position of a body or a particle. So it is defined as that, or you can say it's a straight line joining, because we know the shortest path is nothing but a straight line. So we define displacement as the shortest path of the straight line joining the initial and the final position of a body. So you can say that is how we define it in words. The displacement is the shortest path, or you can say a straight line joining the initial and final position of rigid body, particle, point, moving point, whatever we call it. But here obviously we'll see the vector definition. So obviously we can understand that it's a vector. It has dimension of length. Obviously a vector's magnitude is a non-negative quantity. So the displacement, when we talk about magnitude of the displacement, it can either be 0 or positive. It can never be negative. So that is another important thing to understand, right? And also we see that the magnitude of displacement may increase or decrease in an interval of time. That is something important. So this is a sort of crude way of defining that the displacement. Now coming to the proper mathematical formula, or let's say the vector definition of displacement. Let's understand that. So let's say in our given coordinate frame, this is the position of a particle at a given point of time, and that particle, let's say, travels from A all the way to B through some kind of path like this. So let's say the particle is located here at t equal to t1 time, and then so that might be, let's say when we are starting our stopwatch, so t1 could be 0, and after a certain interval of time the particle reaches here t2, which is, let's say, t1 plus delta t. So that's how time is progressing. So the particle is traveling like this from A to B along that given path in a time interval of delta t. So the example we are taking is particle traveling from A to B in a time interval delta t, that is from t1 to t2 equal to t1 plus delta t. So then how would we define the displacement? So we first of all use a parameter s for it. So how much would this displacement be? As you can see, the displacement would be the shortest path joining the initial and final position. So that shortest path will now be defined as a vector. So in going from A to B, the displacement is defined as this. Okay. So it is the vector joining the initial position, which in this case is A, and the final position. So now we can also think of displacement in vector context is an even simpler definition, and that is nothing but it is a vector joining the initial with the final position of the body in a given interval of time. Now the even more interesting thing here is that since the position of the particle at A is given by this vector, so we can say this is the initial position, and the position of the particle at the point B is R, is that particular vector. So now we can see that even if we had no knowledge about the path, but we have knowledge about the initial position as a vector and the final position as a vector, it is very easy for us to formulate from that the displacement happens to be nothing but the difference of the two vectors. You can see the vector triangle that is formed over here, and in context of that vector triangle, you can see the displacement is nothing but the difference of the vector RB minus the vector RA. So in other words, it is final position vector subtracted from the initial position vector. So it's the difference of the position vectors. Just take that diagram now and discuss. Right, so as you can see, that gives us an even better way to understand the displacement. So the displacement is, or we can say in better terms that the displacement is the final position vector minus the initial position. So for whatever interval of time we are writing the displacement, and of course it is important to understand that displacement is always, it can be only be defined for a certain interval of time. So for a moving body, if I say just how much the displacement is, the statement does not make sense, because I have not defined what interval of time I am talking about the displacement in. So if I say what is the displacement from, let's say 0900 hours to 0930 hours, then the question makes sense, because based on the information about when to when or which interval of time I am talking about, I can define the initial and the final position, and accordingly I can define the displacement as the vector difference of the two. Right, so just make sure you take a note of that, and we'll be underway with the next set of definitions after that. Alright there, so welcome back, and hope we are clear about the definitions of distance traveled, displacement and position and all these interesting things. Subject will pick up, it will become more interesting as we look at applications, okay? But in order to look at applications, we need to understand all the definitions first, right? Pick up this example. Alright, so let's look at this very basic and easy to visualize problem. So it says that you have a particular clock, visualize one of those tall tower clocks or grandfather clock kind of situation. It says that the minute hand of the clock is exactly 0.5 meters in length, half a meter, so that would be about 1.5 feet, so it's something like this, let's say. So as it's traveling, or rather as time is progressing, the various hands of the clock are rotating about, shifting about. So we have to find out the distance traveled by not it, but rather by the tip of the minute hand from 7 a.m. to, yeah. So as time is progressing and the minute hand of the clock is rotating about, we have to find the distance traveled and the displacement of the tip of the minute hand between 7 a.m. and 7:15 p.m. So let's look at the solution of the problem. It's extremely simple. So let's just visualize at exactly 7 a.m., right? Minute hand would be here, and the hour hand would be here. So that's 7 a.m. and at a different time of 7:15 a.m. minute hand would have progressed to this point, and hour hand here. That would be the situation. So let's consider the tip of the minute hand, how that is traveling. So that is the situation, isolating out the tip of the minute hand as a particle. Okay, so you can see that the distance traveled is the length of the path. Okay. So that is basically path length. Okay. So that would be 1/4 of the circle So that would be 1/4 of 2 pi r. Okay. So that would be 1/4 of 2 pi into 0.5 in meters. As you can see, that would be pi meters, roughly speaking. 3.5. So that is as far as the distance is concerned. Okay. Now, as far as the displacement is concerned, within the same thing, you can see that the displacement would be this vector here. So you see that the displacement would have a magnitude of root 2r, just using simple trigonometry. Okay, so see that it has a magnitude of that would be the magnitude of the displacement. Okay. So, for example, if we were to take our XY reference frame like this, it would be enough to take just XY coordinate frame here, because it's a two-dimensional motion. So the tip of the minute hand is traveling within a two-dimensional plane, which is the plane of the clock. So it would suffice to define just a two-dimensional reference frame. So in terms of that, you could see that the displacement could be defined as 0.7 meters into minus cos 45 degrees I cap, so plus minus sine 45 degrees G cap. So basically work out to be, this was root 2 by 2, remember, and this is 1 by root 2 I cap minus 1 by root 2 J cap. So the displacement as a vector is coming out to be 0.5. Excuse me. So that is the description of displacement as a vector quantity in terms of a defined coordinate frame. The rectangular box. Okay. Those are the dimensions, 12 by 4 by 3 meters. Now let's say an insect crawls on the outer surface of the box from E to B. Find the displacement of the box, of the insect, and secondly, the minimum possible distance. Okay, so let's understand this. So the displacement from A to B, let's understand that first. So let's say we were to denote this as our x-axis, this as our y-axis, this as our z-axis. Let's say this dimension is 12, this dimension is 3, and this dimension is 4. So we can see that we would simply define the displacement as position vector of B minus position vector of A. That is the change in position. That's how we define displacement. So we can see that position vector of A would be 3 k cap from the origin to the point A is 3 meters simply moved along the z-axis. Okay? And similarly, the position vector of B you can see is 12 along the x-axis plus 4 along the y-axis. So quite simply, the displacement would be this minus this. So it would be 12 I cap plus 4 j cap minus 3 k cap. And from this we can see that the magnitude of the displacement 144 plus 16 plus 9, so that's 30 meters. So that pretty simply is the magnitude of the displacement, as you can see. Okay. Just take a minute to note that down. Alright, now the next thing we want to understand here is the minimum distance crawled by the insect. Remember, the insect cannot directly fly from the point A to B. So if you think of the displacement, if you visualize the displacement vector, it is the body diagonal of the cube or of the rectangular box. But remember, here we are not talking about the insect flying inside the box along the diagonal. Here we are talking about the insect crawling along the outer surface of the box. So the actual path of the insect cannot be along the displacement vector. So the actual path is in fact some kind of combination of paths along the surface. Okay. So one thing we will simply understand here is that the magnitude of displacement will be quite a bit less than the minimum distance traveled, because the shortest path, being a straight line, is not within reach of the insect. You can say the insect is not in a position to take that shortest path. It's taking a much more long kind of route. Okay, so you'd see that minimum distance traveled by the insect would be, the insect travels straight line followed by straight line. Okay. So if we unfold this rectangular box, so let's say these points are C and D. So this would be the shortest path. Minimum distance, we can say D minimum is so that is the minimum distance traveled. You can see that the magnitude of displacement was 30 meters. So note here that the minimum distance also traveled is larger than the magnitude of displacement. So we're going to be discussing more about this relation between distance and displacement, etc. as we go now. Note this down and maybe take a break.